connection of the alternator. The alternator we have in the lab. So on the stator, basically there is 6 windings, and all the terminals are available on the board, and externally we have to connect. It can be connected as a star or delta form. Now basically we have 6 windings. The terminal markings are like this. This 1 and 4. There is a winding between terminal 1 and 4. Then one between 2 and 5. The next one between 3 and 6. Then between 7 and 10, 8 and 11, 9 and 12. So 12 terminals are available. Now the phasor relationship of the windings are this winding 1, 4 and 7 and 10. These are just in the same phase, and 1 and 7 is the same polarity. For these 2 and 5, 8 and 11 are of same phase, 2 and 8 of the same polarity. Here 3 and 6, 9 and 12 are of the same phase, with 3 and 9 in the same polarity. Now as you have determined the winding position of the transformer, similarly this also can be done. What is the position of the windings and so on. That is simply what we can do, say if we short these terminals and the alternator is driven by the DC motor at a particular constant speed, and if we apply DC excitation to the alternator field, then EMFs will be induced in all the windings. Then the EMFs can be measured. Now if this is the position, then between these 2 terminals the difference is 60 degrees. So if the individual EMFs are V, then this should be V, and this is √3V. This will be twice V. Similarly, again this between these 2 terminals √3V, and this will be V. Now if the terminals are reversed, accordingly that depending on the winding position, the voltage will change. Now as we all know, the alternators normally on the stator we will have star connection, so we will connect the alternator in star form. Now for this, these 2 windings which are in the same phase are connected in parallel. So similarly these 2 are connected in parallel, these 2 are connected in parallel. So we will have 3 sets of winding, then connect them in star. So for this, to connect it in star, just mark that this is 4, 5, 6, 10, 11, 12. These are shorted. 1, 7, 2, 8, and 3, 9 are shorted. And the output terminals are 1, 2, 3 or 9, 8, 7, whatever it is. So these connections has to be connected externally on the terminal board. Now this is the connection circuit diagram for the experiment. So our objective is to determine the parameters of the alternator. So for this we will require a prime mover. So there is a DC motor, shunt motor, which will act as the prime mover. So in the same shaft we have the alternator and the DC motor. This is shunt motor, so it is connected to the starter. So there is a resistance in the field circuit, an ammeter in the field circuit, and the ammeter in the armature circuit. And this ammeter is a center 0 type. And on the AC side, we have 2 wattmeters on 2 phases and an ammeter. Now this and this is the switch. This is actually the synchronizing switch. On this side, we have the bus bar. On this side, we have the alternator. So when we synchronize, say for the zero power factor test, we have to synchronize the machine. Then this switch has to be closed on the synchronized condition. Now for synchronization, as have been discussed in earlier in the first semester, we follow the one dark and two bright lamp method, and also there is a synchroscope. So this lamp 1 is connected between phase A of alternator and phase A of the bus. Lamp 2 is connected between phase B of alternator, phase C of the bus. Lamp 3 between phase C of the alternator and phase B of the bus. This is a two-way switch. On this side, when the switch connects between these 2 points, we will see the bus bar voltage and frequency, and on this, when it is shown on this side, between these 2 points, it will show the generated voltage and frequency. And this is the field of the alternator. The DC supply has to be given. So this is the basic circuit diagram. Same circuit diagram as you have used for the determination of V curves. So synchronized process is also same. That is, we have to control basically. That is generator field, a rheostat in the generator field, and rheostat in the DC motor field circuit. So when we control the field circuit of the field current of the generator, what is changed is the magnitude of the voltage, and if we control the field of the motor, then the speed is controlled, and that will change the frequency. So adjusting these two, we adjust the voltage and frequency of the set almost when the voltage and frequency of the incoming machine and bus bar are almost same. Then when the this phasor, three phase incoming and this bus bar phasor are superimposed, then this lamp will have zero voltage, so this will be dark, and these two will have the line voltage, so equally bright. Under that condition, this switch has to be closed. Now synchronization for this experiment only we will require for the zero power factor test. Other test we will does not require the synchronization. Now the different runs, first run is the open circuit test. Now for open circuit test, we do not have to synchronize, but we will run the alternator at synchronous speed by the prime mover. And we vary the field current so that the EMF is varied in steps of about 10 volt, and vary the EMF up to 150% of the rated voltage. So the plot between the open circuit voltage and the field current will give you the open circuit characteristic. Next is the short circuit characteristic. For the short circuit characteristic, also synchronization is not required. We short circuit our alternator terminal by an ammeter, and again vary the field current in step from 0 in steps, small steps, so that the short circuit current which is flowing through the ammeter does not exceed 25% of the rated armature current. Now this characteristic will be straight line, linear characteristic, whereas the open circuit characteristic is non-linear. Now preferably the voltage should be the synchronous, speed should be the synchronous speed, but however for short circuit it is not mandatory that the speed should be maintained exactly synchronous speed, because as you have studied that the short circuit condition as the resistance of the synchronous machine is very small. If we neglect the resistance, so approximately that voltage which is induced is proportional to the speed, so proportional to the frequency. Similarly, the short circuit, that reactance of the machine is proportional to the frequency. So approximately the short circuit current is which is the voltage divided by the impedance. Neglecting the resistance, it is basically the reactance. So that is not affected by the speed, provided that the resistance is negligible. Now, if the speed is too low, then the reactance is not, the resistance is no longer comparably very small, so that we can neglect. So then error will be introduced. So it is better to keep the speed as synchronous speed or at near to the synchronous speed. So the characteristic what we get will be like this. The OCC will be a nonlinear characteristic following the BH curve. So this will be OCC, and the short circuit characteristic will be a straight line. Now the power phase equivalent circuit of the synchronous machine, we have the resistance and the synchronous reactance. So what happened when we short circuit the terminal, then the EMF which is induced divided by the short circuit current will give you the synchronous impedance. So for any particular field current, the open circuit voltage divided by the short circuit current will give you the synchronous impedance. Now, as the OCC is non-linear, so if we plot the synchronous impedance versus the field current, this will be a non-linear curve. In this linear region, when OCC is linear, it will be more or less constant. But after this, that open circuit voltage is not increasing proportionally, but the short circuit current is increasing linearly. So the value of synchronous impedance decreases. So we can give, and the resistance value, this can be determined by DC voltmeter ammeter method, and we can get the synchronous reactance from this. But however, this resistance is very small, so if we neglect this, approximately what we get is synchronous reactance of the machine from OCC, voltage of OCC for particular field current divided by the short circuit current for the same field current. Now, for a salient pole machine, now the machine here we will determine XT and XQ, so it has saliency. Now, for salient pole machine, actually OCC and SCC, the ratio of voltage and current from OCC and SCC, it will give XD or direct axis synchronous reactance. So for this machine, we will get direct axis synchronous reactance from OCC and SCC characteristic. The next run is to determine ratio of XD and XQ. That is, we will perform the sleep test. Now for sleep test, actually the machine is alternator is run at a speed slightly less than or slightly greater than the synchronous speed, and positive sequence reduced three-phase voltage is applied to the stator winding. The field is open, so as the speed of the rotor and the speed of the rotating magnetic field created by the current flowing through the stator winding is slightly different. So what happens when the field structure is coincident, when the rotating magnetic axis is coincident with the direct axis, in that case the reluctance offered to the flux path is minimal, because here the machine is not loaded. So the current the machine is drawing is mainly the magnetizing current to establish the flux. Now, as both the stator and rotor are iron structures, so most of the MMF is consumed by the air gap. So in the direct axis, as the air gap is small, so the reluctance offered is small. So we have applied a constant voltage, so flux is constant. So for that, creating this flux through the small air gap, we require lower magnetizing current. So current value will be small, and correspondingly, if we measure the terminal voltage at the machine alternator, then terminal voltage is applied voltage minus the drops in the leads and the wires. Now, for smaller current, drop is small, so the voltage is larger. But when the flux axis is coincident with the quadrature axis, then the air gap is large, so reluctance offered to the flux path is large. So we will require a larger magnetizing current. So correspondingly, the drop in the leads and the wire is larger, so the voltage available at the machine terminal, that is applied voltage minus the drop, that is large. So the voltage is small, the drop is large. So basically the ammeter and voltmeter which is connected in the circuit, these readings will vary. It will oscillate from maximum to minimum. Now the ratio of maximum voltage to minimum current should give us xt, and minimum voltage by maximum current give us xq. So ideally both xt and xq can be determined from the slip test. But what happens? This inertia of the moving system introduces some error. When we are reading it manually, there can be some error. Or if we take the oscillogram reading, they are also from the oscillogram, when we are taking the values, there can be some manual error. So to avoid the error, as a reading, the difference is very small, so the error percentage will be large. So to avoid the error, actually what is determined from this test, slip test, is a ratio of xt and xq. And xt, as I have told, is determined from open circuit and short circuit test. And from knowing the ratio from here, we can determine xq. Next, another one is the negative sequence reactance. So that if our supply is unbalanced, that can be divided. We can have a positive sequence and negative sequence voltage. So what is the impedance offered to the offered by the machine to the negative sequence voltage? Now the connection diagram for this will be like this. That is, this is the same star connected stator. The rotor winding is shorted on itself. We have ammeter here, wattmeter, 2 wattmeter and a voltmeter, and what we are applying is a negative sequence, a small negative sequence voltage. So this ABC sequence, input sequence, has been changed. That is the main change. So we measured the meter readings. Now our negative sequence impedance is V. That per phase voltage is V by root 3 because star connected, and this is the current. So V by root 3I. Now cos theta is P by root 3 VI. P is the total power. So Z2 will be, X2 will be Z2 sine theta. So Z2 this value, and from here we can get sine theta 1 minus P square root over of that. So X2 will be this. Putting this value, V by root 3I root over of 1 minus P by root 3 VI square. So this will be 1 by 3I square root over of 3V square I square minus P square. And R2 can be taken as root over of, there's a mistake, it should be square. Z2 square minus X2 square. So these are negative sequence reactance. And another is a zero sequence. So for the zero sequence, we have to connect in series. The connection which was in star, we remove the star connection and the windings are connected in series, and the single phase voltage is applied. So we have a wattmeter, a voltmeter, and ammeter. Here also field is shorted on itself. Now the voltmeter reading by the ammeter reading gives the total impedance of the three phases. So impedance, zero sequence impedance of one phase will be V by 1/3 of V by I. R0, we have the power, so 3 P by 3 I square. So this is if this is I, this also will be I. This A, you can omit. This x0 will be root over of z0 square minus r0 square. So next is the zero power factor characteristic. Now the zero power factor characteristic test, we know that for zero power factor test, the alternator is should be run at synchronous speed, and variable zero power factor load should be connected to the alternator. Now it is not very difficult to have a variable zero power factor load with discrete elements with resistance, reactance. Might not be impossible, but it is very difficult. So we know that controlling the field current, we can control the power factor of the alternator when the machine is connected to the bus bar. So we synchronize the alternator with the bus bar and adjust the field current so that the rated rated current is flowing through the armature, and the field is adjusted so that the wattmeter readings, the total wattmeter reading is 0. So the power factor will be active power is 0. Under this condition, the terminal voltage, field current, armature current, wattmeter readings are noted. Now the plot between the terminal voltage and the field current gives us the zero power factor characteristic if we perform the zero power factor test for different field currents. Now it should be performed at constant current. So for every possible to get the characteristic, but it is a very it is a bit difficult. So normally the zero power factor test is done for 1 point for the rated voltage. This is the terminal volt per rated current only and rated voltage. That is only for 1 point we perform the zero power factor test. Now OCC also already we have performed. Now if we go to the phasor diagram of the under zero power factor condition, say this is the terminal voltage. So terminal voltage plus IERA plus IAXAL, or XAL is the leakage reactance, gives us ER, or the air gap voltage. Now the equation for air gap voltage is ER is equal to VT plus IERA plus JIAXAL. So this is a phasor equation. But in the from this figure, you can see that this angle is very small, actually smaller than whatever I have drawn here. So basically ER and VT are almost in phase because this RA is very small. So ER is approximately VT plus IAXL. So or VT is equal to ER minus IAXL. So this was a phasor equation. It reduces to a scalar equation under the zero power factor condition. Similarly, if we go to the Mmf relationship, our resultant Mmf FR leads ER by 90 degree, and FF, the field Mmf, can be is, and this FA, the armature reaction Mmf is phase with IA. Now, relationship is FR is equal to FF plus FA. So FF, or the field Mmf, is FR minus FA. So we have FR, we have FA. So FR minus FA is will give you FF. So as this FR and FA are 180 degree opposing almost, so FF is approximately equal to FR plus FA. That is, this phasor equation reduces to this scalar equation under zero power factor condition. So as the zero power factor characteristic is a characteristic for constant current. So this from this point, if we draw a horizontal line corresponding to this terminal voltage Vt, and from the one thing we assume, that is OCC actually is the plot between the terminal voltage and the field current under open circuit condition. Now ER, which is the air gap voltage, that is not a measurable quantity under loaded condition. So we considered that OCC, this relationship between ER, or the induced voltage under loaded condition, and the resultant field FR under loaded condition, the relationship is given by OCC. That is OCC actually, which gives the induced voltage and the field resultant field under open circuit condition, also gives the relationship between the induced voltage and the resultant field under loaded condition. Actually, due to the saturation and other drop, there is slight difference, but the difference is very negligible. For practical purposes, we consider OCC gives the relationship between ER and FR. So from this point corresponding to ER, this is the point on the OCC. So if OCC gives the relationship between ER and FR, so this is our FR. And this point is the zero power factor point, so corresponding to Vt. So it is a plot between Vt and but approximately equal to the leakage reactance of the machine. So now, as I told, that the zero power factor characteristic should look like this. Why it is? You can see that it is the same form of the OCC, only shifted downwards and to the right. Now, what happened if we consider this triangle ABC? This is called the Protea Triangle. Now, this is AB is the armature reaction mmf FA, which is constant because IA is constant, and BC is IA XAL drop. This is also constant because IA is constant. Now, so if we shift this triangle parallel to itself, so that this point C always lies on OCC, then this point A should always lie on the zero power factor curve. So the zero power factor curve and OCC have the same form. Now, when this triangle is fitted at this point, that is when this point A falls on the x-axis, then this point, as F dash shown here, this is the short circuit point because the terminal voltage is 0. So this point should be available from the short circuit characteristic. So actually what we do, we perform zero power factor test for this point, and we get this point. Now I draw a line parallel to the horizontal line through this point. Now from the short circuit test corresponding to this constant current, we get this value OF dash. This is the short circuit field current corresponding to short circuit current. Now this OF dash, it is made equal to AD. So in this horizontal line, we cut this value, and through this D, we draw a line parallel to the air gap line. So this line cuts the OCC at point C. So this is the point C. So what we have this 0 power factor point, and corresponding to IA, we have this value AD. Then through D, draw the line parallel to the air gap line. It will cut the OCC at C. So drop a perpendicular from C. So CBA, this will be our Protea Triangle. So from Protea Triangle, we will get this armature reaction MMF for this particular current, and we will get the leakage reactance. Now from this, we can determine the regulation also for some other power factor also. So what we now know, say for the same current for other power factor, we can calculate the regulation. That is VT we have the current, we know the power factor, so we know this angle theta. So IARA and IAXL, IA can be determined separately by DC voltmeter and meter method. So IARA and IAXL is drawn. So we got ER. So once we get ER, from the OCC corresponding to this ER, we can get the value of FR. So at FR, this angle will be 90 degrees. So we can draw FR here. Now corresponding to IA, from the short circuit test, we get this value of FA plus FAL. So we know the angle. This angle can be measured. That is, if this is theta dash, 90 degree plus theta dash plus theta. So with FR, with this angle, we draw this FA plus FAL. So this is the resultant MMF. Sorry, this is the field MMF FF. So corresponding to this FF, we determine EF from the open circuit characteristic, and EF minus VT by VT will give you the regulation. So these are the steps for determining regulation from ZPFC. Draw OCC and SCC, construct the Protea triangle and determine XAL, armature reaction FA, determine ER, from OCC determine FR, construct the MMF diagram and determine FF, from FF determine EF and determine the regulation. Now this is the basic theory. So it is not, I will just show a few hello, can you see the video? Hello?
Yes, ma'am. It hasn't started yet.
Now you can see the screen.
Yes, ma'am.
Yes, ma'am.
Now you can see the terminal block. This is basically the alternator. You can see the machine.
Yes, ma'am.
Yes, as I have told that you can see that there are 12 terminals, and these all 6 we have shorted. এবার দেখা যাচ্ছে আবার? হ্যালো
ম্যাম প্রেজেন্টেশনটা অফ হয়ে গেছে।
শেয়ারিং করে দেওয়া হয়েছে।
কেটে গেছিল তো, মানে মাঝে মাঝে কেটে যায়। ঠিক আছে, আমি আবার প্রথম থেকে দেখাই। So the DC motor, this is DC machine connection. কলেজে করলেই মুশকিল, এত মাঝে মাঝে এত কেটে কেটে যায়। আজকে আমি বিয়ে হচ্ছিল বলে জিজ্ঞেস করলাম একে, বললো না ম্যাডাম সারা ক্যাম্পাসে এরকম হচ্ছে। তাও তো এটা চলছে, ওই ল্যান্ডলাইনটা চলছে না।
ইউনিভার্সিটি লেভেল করে এটা সবথেকে ভালো না, এত স্পিড দিয়ে যায়।
আসলে এটা বোধহয় লোকটা বোধহয় একটু বেশি আছে।
সবকিছু মনে রাখতে হচ্ছিল।
So this is the armature connection. This is the field terminal of the starter. So from here we go to the rheostat here. So after that we have the ammeter. Then these 2 point A2 and F2 has to be shorted. And from here we will have a connection to L1. This is alternator connection. This is 1, 2, 3 is the terminals of the alternator. Terminal of the star connected alternator. So these three, this is the board. So lower side of the board. In between we have the switch that will act as a synchronizing switch. On the upper side we will connect the bus bar. there is a switch in between. So on the upper side, we will connect the password. From there, we should take to the board. This is the meter. This is the watt meter. This is the voltmeter.
frequency meter দেখেন এমনি জাস্ট এটা দেখে করে
This is the two-way switch. What was shown in the circuit diagram. And this is the synchronizing switch. This switch will act as a synchronizing switch. So here we have the 2-watt meter and an ammeter connected. Well, actually, what we have decided that I will give some data. You will make the report on this based on that data and submit it by online. We will go in this mode unless and until we are allowed to take physical lab. Where if we are allowed to take physical class, then we will arrange for physical lab. But for the time being, you submit the report by mail so that we can be prepared for evaluating your lab report. Now, I will take a screenshot for your attendance, so do not leave before I get that screenshot. Yeah, that. Okay, taken the attendance, you can leave now. I will send the files, that presentation file and data to you in the group mail.
Okay, ma'am. Thank you, ma'am.
Submit within 7 days. That is next Friday. Okay.
Okay, ma'am.